Hi, everyone. Thanks for coming to our talk. We're going to give you a brief overview of what we do in Chromium OS firmware. So just a brief introduction. My name is Shelly Chen. I'm a Chromium OS AP firmware engineer.
And my name is Asito Bwaji, and I'm a Chromium OS EC firmware engineer.
So here's a quick agenda. First, we're going to talk about why we think firmware is important. And then Asito will give you a brief overview of what the embedded controller firmware is responsible for. And then I'll talk about the application processor firmware, and we'll follow that up with a Q&A. So what do we do on our computers? The majority of people do three things on their computer. They surf the web, they watch videos, and they check email. So how do we, as firmware developers, help you achieve this goal?
So in order to actually use our computer, we'll need to provide power to the system on a chip, also known as the SoC, which includes the application processor, which we call the AP. Now, the AP is the processor which you can think most of the work is done on a computer. This would be, for example, the Intel Core i5 processor. The EC also participates in power sequencing to boot the SoC such that we can do this work.
So once the EC is fully booted, we'll have enough power to boot up the SoC and start execution of the AP firmware code. And the goal of the AP firmware is to initialize enough things to get the OS up and running. And once the OS is running, you can now surf the web, watch videos, and check email. So this is where our team falls in this boot process. So I wanted to first give you guys a brief overview of how we fit together. So let's start with CR50. CR50 on the bottom left is the firmware that's running on our Google Security Chip, or GSC. It takes care of a lot of security features, like all the TPM functionality that the AP needs, in addition to taking care of hardware write protect. It also oversees something called CCD, or case closed debugging, which controls access to UART consoles for both the EC and AP, which we developers use a lot during development, and also allows us to flash the software on our chips. So next, if we go to the middle top, we have the EC software, which Asita will go into further detail later. The EC takes care of a lot of power issues, like handling the charger and power states, in addition to handling system resets with the help of CR50. It also takes care of charging peripherals through USB-C, or things like a stylus if there's a stylus garage in the device. Also, it takes care of all keyboard-related items and sensor information, like the lid switch, and forwards it to the AP for further processing. So moving on to the AP, or the application processor, on the bottom right, the AP is the firmware that sits on the SoC, or the system on a chip. It takes care of things like graphics and display. It handles the initialization of peripherals, like the camera and touchpad. It sets up the audio for the firmware screens, and it also handles input from peripherals, like the fingerprint sensor. The AP needs to communicate with CR50 because it uses it to execute all the TPM functions for verified boot.
So now I'm going to give a brief overview about the embedded controller firmware. First, I'll talk briefly about what is an EC, what are some of the key EC responsibilities, including keyboard scanning, some of the USB-related ICs, battery charging, buttons, switches, LEDs, and power sequencing. So now I'll be presenting. And again, if you have any questions during this presentation, feel free to drop them in the Slido link above. So, should be seeing my slide about what is an EC. Yes. So the embedded controller is a small microcontroller present on nearly all notebooks. They're typically very resource constrained with about 512 kilobytes of flash memory and anywhere from 128 to 256 kilobytes of SRAM. In Chrome OS, we typically use the ARM Cortex M4-based microcontrollers, although some designs might use something a little bit less common or a little bit cheaper. Examples of this could be the Andy Star architecture in the ITE IT8320 or the STM Microelectronics STM32F0. Our ECs run our own real-time operating system, RTOS, which we call Cross-EC. It's a lightweight preemptive RTOS with static tasks and no heap. Now that you know a little bit about the EC, how about we go over what it actually is? The EC kind of took over some of the responsibilities of the keyboard controller and then grew and got more responsibilities such as power sequence and battery charging. Back in the early Chromebooks, the EC was not running our own OS. And from what I recall, the firmware engineers at the time kept having to go back and forth with the vendor reporting issues. For example, they weren't sure of what the code looked like, but they could say it seemed like the bug was here. And when they would get new updates from the vendors, we would also get new bugs or features. And so later on, they decided it would best to have more control over the EC firmware. So today, our EC codebase supports roughly 9 different families of ECs and microcontrollers from a lot of different vendors shown on this page. And as part of the Chromium OS project, Cross-EC is open source firmware. And now, a lot of these vendors, they went through the code review process. And for example, some of the ECs that we support are the Intel Sensor Hub on Intel devices. On Nuvoton, we support the NPCX5 and NPCX7, which was used on the Samsung Chromebook Plus and also the Google Pixelbook. We've used Texas Instruments ECs before. I believe this is the TI LM4, which was used on the original Google Pixelbook, or Chromebook Pixel, sorry. We've used Microchip as well on some of the HP Chromebooks, ITE with some of the recent, also HP, Acer. This would be the Intel Gemini Lake Chromebooks for education market. ST Micro again on some of the ARM devices. Maxim Integrated and MediaTek on also some of the ARM devices as well. So for a device that could know your every keystroke, since the EC is in charge of keyboard scanning, it's nice to know that Cross-EC is open source and that one can audit the code that's running. And now some of these ECs can execute in place directly from the SPI flash, or their program is copied into SRAM and then executed out of there. So here is a brief overview of kind of the 2 major structures that we have in the EC. So up top, we have the TI LM4. Again, this was using the Google Chromebook Pixel. And then below, we have a Nuvoton flash layout, which was used in the Samsung Chromebook Plus. So we keep 2 copies of the EC firmware in SPI flash. We have a read-only copy and a read-write copy. Now, the read-only copy is locked and secured by the SPI flash write protect signal. And this comes from the final version of firmware that we developed as the device was going into its final production phase. We use this ECRO firmware for recovery because that's the firmware that we can trust. And since it was locked away, we can assume that it hasn't been tampered with. Now, updates can be provided in the form of over-the-air updates through regular Chrome OS updates, and sometimes those might have firmware updates. And as part of the verified boot process, the EC firmware could get updated as well. And Shelley will talk about that a little bit later in this presentation. But here you can see for the TI LM4, it runs directly out of flash, whereas the Nuvoton, it copies an image into SRAM and then runs out of there. Now here, so where does the EC fit in? So here's kind of a crude block diagram of the EC connections. So at the top here, we have the embedded controller, and we have things like the internal matrix keyboard connected, We have the USB-related ICs for the Type-C and Type-A ports. We have miscellaneous buttons and switches, think your volume buttons or power buttons, things like that. We also have sensors, so for example, accelerometer or a gyroscope. We also have the charger IC, which connects to the battery, such that we can actually charge the lithium-ion battery present in the notebook. And then we have CR50, or the Google security chip, which helps with debugging, flashing, and miscellaneous reset. And then we have a bunch of other signals connected to the SoC such that the EC can keep track of the current power state of the system. So, as I mentioned before, some of the key responsibilities for the EC were power sequencing, detecting when the keyboard is pressed and sending those keys up to the AP, powering external USB devices such as your nubbies, mice, cameras, things like that, taking power from AC adapters, charging the battery, and powering the system. But the EC also can detect when the user opens the lid, closes it, and it actually determines the lid angle through vector nav. But now I'll just go into a little bit in detail of some of these responsibilities. So here we have a standard Chrome OS keyboard layout. It may not look like your typical QWERTY keyboard layout, but this is the underlying circuit in which the EC connects to the keyboard matrix. You can imagine that the US QWERTY glyphs would be printed on here. So for example, this key number 31 would be where the A key is on US QWERTY keyboard layout. And that would correspond to this matrix location here. And so there are a series of columns and rows, and these all connect to the EC. And the EC can detect when a key is pressed, and then it scans the entire keyboard matrix to see what keys change state. So for example, the columns are driven, and which the EC outputs a voltage, and then it reads each of the rows to see what would change. Once it figures out what changed, it can generate a scan code and send that up to the AP such that when the user would press www, the EC detects that the W key was pressed and then sends those scan codes to the AP to be shown on screen. Now here is a USB Type-A receptacle. The EC controls power to the USB-A ports on the system, and basically it's very simple. When the system turns on, it applies power, and when it turns off the power. In addition, the EC can configure these USB-related ICs for what we call the USB battery charging version 1.2. And that allows the Type-A port to supply higher current. By default, USB 3 ports are limited to 900 milliamps, but with BC 1.2, or battery charging version 1.2, you can up that all the way to 1.5 amps. In addition to Type-A ports, the EC is also in charge of Type-C ports. So here is the Type-C connector. Now, USB-C is a versatile connector that allows for simultaneous high power charging and data. With USB Type-C, you get USB power delivery, also USB PD. And with the USB power delivery, the same connector can actually provide up to 100 watts of power. And so the EC participates in the negotiation and detection of cables there, as well as also communicating with docks to configure alternate modes, such as DisplayPort alternate mode, such that you can plug in a USB-C powered monitor or a dongle and have display being shown out the Type-C port. On the bottom here is one of the high-speed switches in which the EC configures depending on what is connected. If it's just pure super speed USB, or if it's just pure DisplayPort, or if it's a dock that has both. It can configure these lanes accordingly. In addition, the EC also supports parts called PPCs, or power path controllers, and those are used for overcurrent protection as well as undervoltage protection. Another one of the responsibilities of the EC is battery charging. So here we have just a simple buck boost battery charger in which the power flows in through here, and through some combination of switching of these transistors, dumps current into the battery here. Using the negotiated PD contracts, the EC configures the charger IC to provide the desired voltage and current to the lithium-ion battery pack. It also monitors the battery pack to ensure that charging is safe and that the battery is being charged within the right temperature range. Also, the EC is responsible for button switches and LEDs. So on the top here is, I believe, Cave, which I think is the Asus Chromebook Flip C434. And pretty much everything on this side, with the exception of the 3.5mm headphone jack, the EC is involved in. We have the power button, which also has an LED inside, and we have volume buttons. The EC can detect when these buttons are pressed, debounce them, register the state, and send them to the SoC. The EC also controls LED behavior on the device. Generally, they're used for conveying charge state or power state, such as the device is sleeping. But with fancier components like the segmented light bar on the Google Chromebook Pixel, the EC can control that and show really cool patterns. Lastly, the EC is also in charge of power sequencing. So here's an example of a random Intel x86 timing diagram. And going from top to bottom, it illustrates the order in which various signals must be asserted to turn the AP on. And all of these signals must come up in order, and you'll notice that some of them have little timing footnotes associated with them, and meaning that the timings must be respected for proper SoC operation. Now, some of these signals the EC is involved with, where some voltage rail power might come through the EC verify it's good, and then pass it forward towards the AP or the rest of the SoC. So for example, here is Zumbini, which was an Intel Cannon Lake reference design that we did. And here's the EC. And again, here you can see some of the signals come straight into the EC, and then they are passed through to the SoC. And some of the sleep signals come from the SoC, telling the EC what state the system is in so that we can configure USB ports appropriately. But once all the power is good and we've gotten the SoC into the S0 or fully running state, then we can do some of the really fun stuff that you do on a computer. And so now I'll stop presenting and let Shelley continue.
Thanks, Asita. So now that you have a good idea of the role of the EC, let's discuss what the application processor, or the AP, does. So just a brief overview of the topics that I'll go over. First, we'll go over the different boot modes that we support. And then we'll give a brief overview of verified boot. And then we'll talk about the anatomy of the AP firmware. And lastly, we'll go over how updates are done in Chrome OS. So first, I wanted to remind everyone of Chromium OS's core principles, the 3 S's: speed, security, and simplicity. So if we tweak these a bit into the Chromium OS firmware core principles, we can rephrase the 3 S's to boot quickly, verify everything, and reuse as much as possible. And I'll go over how we apply each of these in our firmware design. So let's first talk about booting. Chromium OS has 3 different boot modes. Let's briefly go over each of their use cases. So first, there's normal mode, which is the standard way Chrome devices boot off the shelf. And this guarantees that you're booting a properly signed image. And we also have recovery mode, which is what we use when something goes wrong. And finally, for our hobbyists, we have developer mode, which allows them more flexibility to customize their devices. So let's first go into the most common boot mode, what we call normal mode, or sometimes also referred to as verified mode or secure mode. Now, this is what consumers get on their devices when they pick them up from Best Buy or any other electronics store. Normal mode enforces the use of signed images. This ensures that the user is not running compromised software and is enforced by verified boot, which we'll talk about later in this presentation. If there are any issues detected during normal boot, then the device will boot itself into recovery so the user can go through the recovery flow. We target less than 1 second from first firmware boot to kernel jump and less than 8 seconds to the login prompt. And we do this by initializing the minimum amount of hardware possible. For example, in normal boot, we don't initialize graphics or audio because there are no firmware screens to be displayed. So our next boot mode, recovery boot, is what you'll see if something goes wrong during the boot up of your device. To the right is an example of the screen that you'll see if your device is booted into recovery mode. Recovery mode allows the user to recover or reset their device without having to go through the trouble of RMAing or sending their device back to the manufacturer, which would leave the user without their computer for several weeks at least. Some possible problems that would cause you to boot into recovery mode are verification failures, or if your disk image gets corrupted, or even if you encounter a hardware issue, like if your SSD is not detectable. We also allow you to manually trigger a recovery boot. Some people do this because they want to install a different version of Chrome OS than what is available on the latest AU or auto update. To manually trigger recovery, we use what we call the 3-finger salute, and this varies by form factor. On Chromebooks, we hold down escape refresh power. On tablets, we hold down volume up, volume down, and power buttons for 10 seconds. And on Chromeboxes, we press the recovery button, press the power button, release the power button, and release the recovery button. So as I mentioned, if you go into recovery, you see the screen on the right, but we recently updated our screens. So if you try to boot into recovery on older devices, you'll see a screen that looks like this. So the last boot mode that we support is what we call developer mode. And when this mode is enabled, kernel verification is disabled, meaning that you can boot Chromium OS images that are not officially signed, such as an image that is self-built. During developer boot, we always display the developer warning screen, and an example of this is displayed on the right. And this ensures that the user will know if they're booting into developer mode, preventing some attacker from switching their device into developer mode without the user's knowledge. We require physical presence to switch a device into developer mode, and that means that the person doing the switch actually possesses the device. And we require confirmation through a trusted source, and this also varies by device form factor. On Chromebooks, it's the Enter key for the attached keyboard. On tablets, it's the attached power button, and on Chromeboxes, it's the recovery button. Many developers enable developer mode because it gives them access to additional features not available in normal mode, including the root shell. It allows them to boot non-official OS images. It allows them to boot from the USB, and it allows them to use the alternate bootloaders, which facilitate the booting of non-Chromium OS images. So as with the recovery screens, we recently updated the developer warning screens. So you see the newest screen on the right, but if you go into dev mode on older devices, you'll see something like the following. So now that we've talked about different boot modes, I wanted to go through our security measures in firmware. In Chromium OS, we use something called verified boot to guarantee the security of the system. With verified boot, we're able to guarantee to the user that they're using a signed OS image. Verified boot also allows users to reset or recover their devices without going through the arduous RMA process and losing access to their devices for long periods of time. Verified boot also lets us disable verification to give developers the flexibility that they want to boot different images. So this is the verified boot flow for a normal boot. Read-only firmware is our root of trust. It's flashed once in the factory, and then hardware write protect is enabled by CR50. On older devices, hardware write protect is enforced with the write protect screw. So in the case of CR50, as long as it's powered on, it can keep the write protection enabled. And we guarantee the security of the device for up to 5 minutes, meaning that if some attacker physically gets a hold of the device for more than 5 minutes, then they can disable the hardware write protect. Read-only firmware contains all the functionality that we need to perform a recovery boot, and this guarantees that if we wipe everything writable on the device, we can still boot the system into recovery and perform a recovery flow to get the device back up and running. The read-only firmware also contains the keys that we need to verify the read-write firmware image. So once we know that read-write firmware is trusted because it was verified by read-only firmware, we can use the keys in read-write firmware to verify the kernel image and boot that. Along the same lines, once we boot up the kernel, we use the hash in the kernel to verify the root file system. And once the file system is verified, we can now start using the tools and applications on our Chromebook. So now that we've covered how firmware ensures the security of our images, we can move on to how we simplify things in the firmware by reusing as much code as possible. So first, let's go over how firmware is organized. At a high level, we have 4 basic components: CoreBoot, depthcharge, viboot reference, and the vendor blobs. Recall the boot flow diagram that we just went over. So this is where the different components fall in the RO-RW split. During boot, we first boot CoreBoot in RO, and then run the RW CoreBoot code to finish off the hardware initialization. After CoreBoot finishes execution, we run depthcharge to boot the kernel. The vendor blobs are used by CoreBoot to help with hardware initialization, and viboot reference is a library used by both CoreBoot and depthcharge. So let's talk about CoreBoot first. CoreBoot is a BIOS replacement. It's open source under the GPL v2 license, and its goal is to initialize the minimum amount of hardware to get a full-featured OS to run. It does things like memory training, setting up GPIOs, setting up the ACPI table, and setting up wake events. Also, it is fast. A lot of effort has been put in to optimize the code and cut down on wasted time, which is why we can jump to the kernel in less than a second. And this is a requirement that we have for every board before launch. CoreBoot is set up as a baseboard variant model, which we use to optimize code reuse. The majority of the configurations are set up in the baseboard files. Variants are defined as variations of the baseboard, and they have the option of overwriting or adding to select configurations. For example, let's take a look at this diagram of the hatch family, which is what we call the devices that use the Intel Comet Lake U SoC. So Google developed the hatch reference board, which uses the hatch baseboard files. Let's say one of our OEMs, for example, Samsung, wants to develop a Comet Lake U Chromebook, but with an AMOLED display instead. So Samsung would start with the hatch baseboard files that Google developed, and then override the display settings to accommodate this AMOLED screen. And the same is done for our other OEMs, like ASUS, who wanted a Comet Lake View Chromebook with quad speakers. Acer, another one of our OEMs, they actually wanted a Comet Lake View device that was very similar to the reference board. So they stayed pretty close to that. And lastly, HP wanted a Comet Lake View device with a different keyboard. So this baseboard variant model makes it really easy for us to develop a large number of variants while minimizing new code and maximizing common code, making maintenance and debugging much, much easier. So now moving on to depthcharge. Depthcharge is the bootloader portion of the AP firmware. It's open sourced under the GPL v2 license. Its sole goal is to boot Chromium OS as quickly as possible. It sets up graphics and sound for the firmware screens and the storage device, like the SSD, for the kernel image. It verifies the kernel selection slot and jumps to it. Additionally, it handles the different boot modes that we talked about earlier. viboot reference is the library containing everything needed to run verified boot. CoreBoot uses it to verify the RW firmware slots, and depthcharge uses it to verify the kernel partitions. Additionally, it contains some logic for navigating the firmware screens and also performs EC software sync, which is when the EC firmware gets updated. And lastly, we have the vendor blobs, and these are not open sourced. They contain vendor-specific proprietary information about the SoC. For example, we have some blobs that help with memory training and also with initializing the SoC. So the last thing I wanted to go over are called OTA updates, or over-the-air updates. Chrome OS updates are released every 6 weeks. Firmware updates are bundled with OS updates, but not as regularly. They are released on an as-needed basis. We use updates to release new features and bug fixes, and we support devices through updates for up to 8 years. So let's go over how updates are done in Chrome OS. So if you recall the boot flow diagram from earlier, we want the update process to be as minimally disruptive to the user as possible. So as a result, we have 2 copies of everything that's updatable, which means all the RW components, including the firmware, kernel, and file system, which I've left out in this diagram for simplicity. So let's assume that we're currently running slot A for both the firmware and kernel. While the user is happily doing their work on the slot A images, the Chromebook communicates with the server and starts downloading a pending update and overwriting the RW firmware and kernel images in slot B. After we're done writing, the switches in NVRAM and GPT are set to slot B for the next boot. So let's say the user finishes up whatever they're doing and they shut down their computer. When they turn on their computer the next day, the RO firmware will try to execute the RW firmware B image, followed by the kernel partition B. After we successfully boot up, slot B will be marked successful, and all future boots will use slot B from now on. And just to be clear, RW firmware image A is not locked to kernel partition A. I'd removed those diagonal paths in previous slides to reduce confusion in the diagram, but wanted to point out that we can update the kernel partition independently of which RW firmware slot we're using. So the image in RW firmware slot B, for example, can be used to verify the image in kernel partition A. So just a brief summary of our Chromium OS firmware core principles. We went over the different boot modes and how we are able to boot quickly by optimizing out all unnecessary functionality. We guarantee the security of the image that the user is on in normal mode through verified boot. And we simplified the design of our code so that we can reuse as much as possible, which makes both maintenance and debugging much, much easier. And that is how we in firmware are able to achieve the 3 S's from the Chromium OS core principles of speed, security, and simplicity. And now we can open up for questions. Okay, so if there are no questions, then thank you very much for listening to our talk. And take care.
Thanks, everyone.